Hello everyone, I am Anikate Koul and today we'll be discussing the 12th problem from the CP-31 sheet by TLE Eliminators under the 1200 questions. So I'll be moving to the CP-31 sheet and we can see that the 1200 parameter has been checked. So I'll be moving down to my 12th problem and we can find a clickable link to our question, friends and the restaurant. So let's begin. The problem statement is as follows. A group of n friends decide to go to a restaurant. Each of the friends plan to order meals for xi bulls and has a total of yi bulls, where I lies between 1 and bulls is basically a currency. So the friends decide to split their visit to the restaurant in several days. Each day, some group of at least two friends goes to the restaurant. Each of the friends visit the restaurant no more than once. That is, these groups do not intersect. These groups must satisfy the condition that the total budget of each group must be not less than the amount of bills that the friends in the group are going to spend at the restaurant. In other words, the sum of all xi values in the group must not exceed the sum of yi values in the group. Now they ask what is the maximum number of days friends can visit the restaurant. For example, let n equals to 6 friends for whom x is this array 839245 and y is this array 531450. Then first and six friends can go to the restaurant on day first according to this calculation because they will spend 13 bills but they have a total budget of 15, so there is no issue with that. And the friends with indices 245 can form a group and they will spend a total of 9 bills, but the total budget would be equal to 12, so they can form a group as well. It can be shown that they will not be able to form more groups, so that each group has at least two friends and each group can pay the bill for this specific case. Right. Now, they've also mentioned that the maximum number of groups the friend can split into is 2, and it is also possible that some friend, that is third in this case, may not visit the restaurant at all. So it is not necessary for every friend to visit the restaurant. Now output the maximum number of days the friends can visit the restaurant for given x and y. Right. Now coming to the input format and the constraints, the first line of a test file would contain an integer t denoting number of test cases, and that can go up till 10 power 4. Then for every line, for every test case, the first line would be a single integer n denoting the number of friends, and that can go up till 10 power 5 starting from 2. And then the next line would contain exactly n integers denoting the x values of the friend or the amount of bursts that they're going to spend for each friend. And then the next line would contain again n integers which would denote the budget that each friend has. Right. Now it is also given that the sum of n values over all the test cases does not exceed 10 power 5. Now you have to output for every test case the maximum number of days to visit the restaurant. If friends cannot form even one group to visit the restaurant, print 0. Right. So as you have read the question, let's discuss it again so that we are clear. Right. So for every test case, we are given three things: n, x, and y. N is an integer which denotes the size of these two arrays x and y. So these two arrays respectively they denote the following things. So x is denoting the budgets. So it's an array which denotes the budgets, right? And y is okay. Sorry, so I have messed up the order. X is actually the spend or the spending amount for every friend, and y is the budget. So don't get confused. This is the spending amount or the amount that each friend is going to spend in the restaurant, and y is the budget or the amount that he can spend, that limit he has. Right. Now both of them are arrays, and now you are asked that each day a group can visit, but the group should be at least two friends, so it can be two or more. Now let's say two people visit, right? So these two people are, let's say, person one and person two, right? So person one has a spend of x1 and a budget of y1. Person two is going to spend x2 and has a budget of y2. So now when they go together, what would happen is they're going to spend a total of x1 plus x2 bills, right? This is their total expenditure, and y1 plus y2 is their total budget, right? Now, for them to successfully visit a restaurant together on some day, it should hold the condition that y1 plus y2 should be greater than equal to x1 plus x2. This is the condition. Now, I have just written this condition for a group of two people, but this can be generalized to any size as well. So, let's say k people visit on a single day, then the condition that should hold true is sigma yi, where I goes from, okay, I should not write sigma because they may not be continuous indices. It would be better that I would write something like this, that y p1, so y of person 1 plus y of person 2 plus y of person 3, so on till y of person k should be greater than equal to x of person 1 plus x of person 2 plus x of person 3, so on till x of person k. So this condition should hold true where I've generalized the number of people that can go on a single day. So there is no limit, there's no upper bound, but there's a lower bound. There should be at least two people, but it can go up till any number. Now what you have to do is maximize the number of groups, right? So maximize number of groups. So you have n people, at least two people should go on a single day following this given condition, and you have to maximize such groups, the number of such groups. Right. Now, as we have seen the problem statement, let's discuss a sample case so that we're able to understand it better. Now, n equals 6 case, I think, has been discussed in the problem itself. So we can choose a different case. Let's say I choose this one. Paste it here. Let's increase the font size. So this is visible. I think I missed a 3 here. Right. Let's increase the font size as well. Right. So the size is 3. This is n, this is x, and this is y. Now let's form some random groups and check for each group, is it possible for them to go together or not. So let's say the first two people go together. So the total expenditure would be 2 plus 3, that is equal to 5, and the total budget would be 1 plus 3, that is equal to 4. So you can see the expenditure is greater than the budget, so this cannot form a group, right? So the first two people cannot go together. Let's try for the first and third person, right? So the total spend would be 2 plus 7, that is equal to 9. The total budget would be 1 plus 10, that would be equal to 11. And this does follow the condition that 9 is less than equal to 11. So this is fine. They can form a group. Let's say the second and third person go together. So 3 plus 7 is the expenditure, that is 10, and 3 plus 10 is the budget, that is 13. So again, this is less than equal to, so this can go, right? This is pretty good. So we saw that the first group, which is the first and second person, that is not possible. Second, this is, I think, second and third. No, this is first and third actually. So let's do this here properly. So the first and third person, if they form a group, they can go together. And if the second and third person form a group, they can go together as well. Let's check if all three of them go together. So the total expenditure would be 2 plus 3 plus 7, that is equal to 12. And total budget would be 1 plus 3 plus 10, and that is equal to 14. That is again less than equal to 12 is then equal to 14. So, right. So, if even 1, 2, 3, all of them go together, even then it follows the condition. So, that is good to go. Now, in any case, you can see that even if two people go together, the third person is left alone. So, uh, we know that a single person can't go to a restaurant. So, in any case, your answer would be 1, right? So, that is also the answer in this case. Great. Now, let's discuss a solution. Okay. Before coming to the solution, I think we should also discuss the time complexity or the expected time complexity because that is quite essential to solve the problem. Now, let's look at some facts. So, first of all, we know that sum of n overall test cases is less than equal to n power 5. This is quite important. Now, this means we can write the total time complexity of the form of O of f of n and not as O of p into f of n because we have a bound over sum of n. So, there is no meaning of including the t in the time complexity notation. Right? So if I write it as of the format O of f of n, then if I write a algorithm that runs in O of n, then this would take approximately 10 power 5 computations. O of n log n would go up till 10 power 5 into 20 approximately, and that would be 2 in 10 power 6, and O of n square would take approximately 10 power 10 operations. Now, we also know that on Codeforces in 1 second, we can run approximately 10 power 8 elementary operations. So, keeping this number in mind, we can say that O of n will run pretty comfortably. O of n log n also runs pretty comfortably, but O of n square can't run because 10 power 10 is much greater than 10 power 8. So, this means that our expected solutions should run in the vicinity of n to n log n, but not n square, right? Now, as you have discussed the expert time complexity, we can move on to the solution. So, before discussing the actual algorithm, we need to figure out what would be the ideal number of people in a group. We need to figure this out because in any case, we need to maximize the number of groups, right? So, if we want to maximize the number of groups, in some way, can we say that we want to minimize the number of people in one group? Because obviously if we have more people in one group then we'll have lesser number of groups because n is fixed, the number of people are fixed. So if we have more people in one group that means we'll have less groups, right? But this is an intuition, but can we prove it? Is it possible for us to prove that, let's say if three people form a group a, b and c, right? Three people form a group, they have their x values, so x a y a, x b y b, x c y c. Let's say when these three people form a group, it is possible for them to go together on a single day to the restaurant. What does that mean? That means that ya plus yb plus yc is greater than equal to xa plus xb plus x. So this is our assumption, right? We are assuming that a group of three people can go together on a single day to a restaurant, right? So if this is true, then this should also be true that ya plus yb plus yc is greater than equal to xa plus xb. Now we want to prove that even if a subset of these three people, and being more specific, that a subset of size 2. So let's say if A and B go together, or B and C go together, or A and C go together. I want to prove that at least one of these groups will also be valid. And that means they can go together on a single day to the restaurant. I'm not saying all of them, but at least one of them should also follow the condition that their sum of y's should be greater than equal to their sum of x's. So let's see how does that work, right? So I have A, B, and C, and for A, B, and C it works, right? Now one case could be that XA is less than equal to YA, XB is less than equal to YB, and XC is less than equal to YC, right? This is one possible case, right? If this is the case, then any group you form of size 2, let it be AB, or let it be BC, or let it be AC, it can go, right? Because if you choose any subset, it will follow the condition that sum of y is less than equal to sum of x. So if this is the case, then all of them are good to go, right? This was pretty simple. But let's take a case where this is not so simple, right? Let's take a case where XA is greater than equal to, oh no, I should not use greater than equal to, I should use greater than, strictly greater than YA, and the rest to remain the same, right? This could also happen. These three conditions hold true, and it also follows the condition that I mentioned above, that YA plus YB plus YC is greater than equal to XA plus XB plus XC. But in this case, we can see that if we form a group between B and C, then here YB plus YC would be greater than equal to XB plus XC, right? So in this case, we found out that B and C can form a group. So we proved it for this case as well. And you can prove another two cases with this. What are those two cases? That XA less than equal to YA, XB greater than YB, XC less than equal to YC. So in this case, A and C can go together, right? Similar logic. And another case could be XA less than YA, XB less than equal to YB, and XC greater than YC. So in this case, A and B can go together, right? Pretty simple. Now let's take a case where two of them have this greater than sign, right? So let's take a case where XA greater than YA, XB greater than YB, and XC is less than equal to YC, right? If this is a case, it should always follow that YA plus YB plus YC is greater than equal to XA plus XB plus XC, because that is assumed. This is our assumption. This should always hold true. If both of them hold true, that means even if I take these two, it should work out, right? Because let's prove that formally. Because if YA plus YB plus YC is greater than equal to XA plus XB plus XC, but YA plus YB is less than XA plus XB. How did I get that? Using these two conditions, right? So using these two conditions, can I say that YC, so let me write it properly, YC plus YB would be greater than equal to XA plus, XB plus XC. Can we say that? It would be pretty simple, right? Using these two conditions, we can pretty simply say that YC plus YB would be greater than XB plus XC, or XC plus XB, both are the same thing. We can also say that YC plus YA is greater than equal to XC plus XA, right? These both of them will hold true. Pretty simple to understand using these two conditions, right? So again, in this case, I have proved that a group of two, at least one group of two will satisfy, right? And you can change around the signs, mess around the signs, take this one here or take this one here. It won't matter, it will be pretty similar. One case is not possible, XA greater than YA, XB greater than YB, and XC greater than YC. This is not possible at all, because if this is the case, then our assumption, or this assumption, can never be true, right? Because if all of these three conditions are true, then this assumption can never be true. So keep that in mind. So we have formally proved for every case of the three people that we took initially, we proved that a group of two people which follows our conditions is always possible. And if you have proved it for a group of three people, You can generalize that for a group of k people where k is a random number, and you can always prove that it is always optimal to take a group of two people only, not three, not four, or not a bigger number. So we have proved this, right? Now, once we have proved that we only want to take groups of two people together on a single day to a restaurant, that also means it is quite simple to land on a algorithm. So what we are going to do is something like this. Firstly, I will take all these values yi minus xi for all I between 1 and n. Right. I will calculate this value. Right. The budget of that person minus the amount that is going to spend. Right. Now think of it in this way, that if this value is greater than 0, greater than equal to 0, that means this person has more money than he's going to spend. Right. And if it is less than 0, that means this person has lesser money than he's going to spend. So if this is the case, if yi minus xi is greater than equal to 0, then this person can be paired with some guy who has yi minus xi, or I should not use I because this is a different person. So I can pair him with a person yj minus xj is less than 0, right? It is possible for some cases. I'm not saying for all, but it's possible for some. Because let's say if yi minus xi is equals to 5, I can pair him up with another guy whose yj minus xj is equals to minus 4. It is possible. Because if I add these two equations, I get yi plus yj minus xi plus xj is equal to 1. So these two people can go together, no issues. Similarly, if a person has yi minus xi less than 0, so I have to pair him with a person for whom yj minus xj is greater than 0, greater than equal to 0. These two conditions are given, but you have to be more specific, right? A little bit more specific, because this is not always true. Let's say yi minus xi equals to minus 10 and yj minus xj equals to 5. They can't go together, right? So I have to be a bit more specific. So what I can actually write is, let's say val of I denotes yi minus xi. So what I'll do, I'll take a person I. So I've taken a person I, calculated this val I, which is yi minus xi. Now I have to find the smallest value val j such that val I plus val j is greater than equal to 0. So I have to find the smallest val j such that val I plus val j greater than equal to 0, and I can pair them, right? And if this val j does not exist, I will simply leave out this person, because I have the room to not take anyone into the restaurant, right? So it is not necessary that I have to take everyone at some day or the other to the restaurant. I can leave out some people as well. So if there does not exist any val j for this val I will simply leave out the val I. No issues. Otherwise, what I'll do is I will find the smallest value val j such that val I plus val j is greater than equal to 0. Now, how will I do this? Again, pretty simple. I can use lower bound, upper bound. So if I store all these values in sorted order, then I can use lower bound to find this value. And every time I find a suitable val j for my val I increment my answer by 1. And at last, I print out the answer, and that is my solution done. Right. Now, let's discuss the time complexity of our approach. So what I'll be going to do is, you can do it in different ways as well, because one way is to sort my array after I calculate these values. So let's say this is my array of values and I sort it, and then I can use two pointers of some sort to calculate this. Otherwise, I can also use a multiset. So I can use multiset. So write it in a better way. Multiset and I will push all my values into it. Right. Now I'll iterate to the multiset. So I'll take one value. So this is a value in my multiset. I'll remove it. So first I'll remove it. Then I will find the lower bound of this value in my multiset. So lower bound. If the lower bound exists, so if it is not the dot end iterator, that means there exists a lower bound. So I will remove that lower bound as well, and I'll increment my answer. And I'll keep doing that until the size of my my multiset is greater than equal to 2, right? Or you can say greater than 1. Both are the same. Because if there is only one element in the multiset, you know that that person cannot go alone. So there is no use of iterating over a single element, right? So at least when it is greater than 1, the number of elements, I can iterate and I can do the above algorithm to check if my answer exists for some value or not. So as we have discussed the solution, we can move on to the implementation part. So the implementation is pretty simple as well. So first I'll take the input of my test cases. Then for each test case, I will take input as the size or the number of friends. Then X and Y, they're self-explanatory. So they'll store the Xi and Yi of each person. I have taken the input here. So we know taking input is O of n here and also here. Now I define my multiset. I've named it MS. So initially what I'll do, I will insert all these values yi minus xi, which I termed as val I. So these all values will be inserted into my multiset, and this will take a time complexity of O of n log n, right? Because each insertion takes log n time, and we are doing n insertions, so it will be n log n time. Now this is my answer variable, which I'll be outputting in at last. So again, while the multiset size is greater than 1, what I'll be doing is I'll be removing the first value. So here you have the liberty. What you can do is you can also first remove the last value and then take a lower bound according to it, or you can remove the first value and then take a lower bound according to it. It is uh, the same. It won't make a difference. So, but we know that in a multiset, the dot begin will give you the smallest element in the multiset. So I take out the smallest element and then I erase it. So erase operation is login. So this operation is O of login. Now I take a lower bound of minus val1 because what I want val1. So this is val1. So I take the lower bound of minus of it because let's say if this lower bound gives me val2, then I will know that val2 plus val1 is greater than equal to 0, right? Because if val1 is positive, then what will happen is this value would be negative, and lower bound of a negative value always gives a value which is lesser than it, right? So if I take a lower bound of minus 3, it will give me minus 3 or minus 2 or something like that. And if this value is negative, then this value will become positive, right? So if it is minus 2, let's say, this will become 2, and a lower bound of a positive value always gives me a value greater than it. So 2 will give me 2 or 3 or 4. So this will always work. That val2 plus val1 will always be greater than equal to 0. So that is a neat trick to find the values. And also we need to remember that lower bound also takes O of log n time. Will log n where n is the current size of the multiset. Now, if this value does not exist, there can be a case where this value does not exist. So I'll simply continue and remember that I don't insert this value back, because if the lower bound does not exist for this value, that means if I am only making groups of 2 people, this person can never go to the restaurant while satisfying the condition. So I just continue. And if there is some value, then what I do, I increment my answer and remove the val2. So this is the val2, I remove it. And in a multiset, always remember erase by iterator, because if you erase by a value, then it will erase all the occurrences of that value, and you don't want that. You want to erase only a single occurrence. So always erase by iterator. and this will also take O of log n. At last, I just simply output my answer. And also to remember, this while loop then will take O of n log n time, because it will take log n complexity per iteration, and the number of iterations would be equal to the size of my multiset. So that is n log n, right? So now coming to the total time complexity. So the total time complexity for this solution would be n log n, and the total space complexity would be O of n, because we're just using linear space in the form of the x and y arrays and R multiset, right? Uh, in the end, I would like to state two things. The first thing is that this is not the only way to implement it. You can also use a two pointer to implement it, but the time complexity would be same, because in the two pointer approach you would have to sort the array while before applying the two pointers. So not a big difference, but that is also a way. The second thing would be, I would like to state, the problem was quite fascinating, because first thing, it had various ways of implementation, so you can try all of them out. The second thing was, it had a really great and login idea of sorting the values and then using lower bound upper bound to find the best pair, and also to prove that always a pair of two is the most optimal. That is a very great observation, and observations like this help to build up your intuition so that you can solve problems like this faster. So thank you, and I hope you like the problem.